Whatever. Yeah, like, what is this?
No, being okay.
The streaming services?
I would just go off of ours because ours are synced before they so
Yeah, because this is electronic, you know?
yeah.
This is electronic. Guess everybody is done with the attendance. Okay. So before I start about I start about the compartmental model, I just wanted to give you an idea what is compartment. When I was a pharmacy student, I never understood compartmental model. So I got this idea about when I went to graduate school. So when we talk about compartmental model, it is nothing but a theoretical it is an assumption. So when we think about a compartmental model, we have to forget about human body. Do not try to relate it human body. So when I was a pharmacy student, I was always trying to think about where is the compartment in the body, how it is two compartment. So always you have to think these are theoretical compartment, like this tank. Okay, this is one compartment. There should be something here, right? So this is your one compartment. Okay, you have to always think that you are playing with two tanks of water, two water container. So you are putting the dye inside here. Okay, and then always you have an opening here. You are opening here, so dye is coming out of this compartment. Okay, so this is called central compartment. Central compartment. Okay, and one of the characteristic of central compartment is that elimination always happens from the central compartment. Elimination is going to occur from central compartment. Okay, so but with this central compartment we have another compartment. So we have another compartment, and then in this dye is also going to the other compartment. So always you just imagine there is nothing. In fact, this pharmacokinetics thing is not about human body. It is about all theoretical assumption. How it reflects a lot of those things, but it is theoretical assumption. Always you have to think. In graduate school, we did a lab on this. So you mix this and you'll see that a drug is coming out. Of course we did not use the drug, we use a dye. Here drug is coming out. This you will consider central compartment. And also here you have another tank of water, so drug also going to that compartment. This is called distribution phase, because so you have to think about this central compartment is your blood or plasma. This compartment is your plasma. Okay, you have drug goes first to the plasma. So this is your plasma. So from plasma it is going to other compartment, other tissues. This is called peripheral compartment. Next year I will make this picture much better. Peripheral compartment. So as a result, what is happening here? So what is happening, you see in this case, here if you look into this figure, the concentration of the drug is going down in the central compartment. Because you see here, it is eliminating, and also it is going to another compartment. So drug is going down. But this peripheral compartment, as you see, the concentration is going up, but at certain point, they equilibrate. So this phase is called distribution phase. This is called distribution phase. Okay, so this is called distribution phase because, and one of the observation here is that during the distribution phase, there is a rapid decline in blood drug concentration. There is a very rapid decline in drug concentration because drug is going from central compartment to peripheral compartment. Okay, and so now what are those, as I have mentioned, this is plasma is your central compartment. Peripheral compartment, you can assume, which does not have lot of blood perfusion like muscle, fat tissue. So these are called peripheral compartment. So always you have to remember, we have two compartments, central and peripheral. In case of central compartment, drug elimination occurs always from the central compartment. Okay, and there is a distribution phase. During the distribution phase, there will be a rapid decline in drug concentration, because you see why there is a rapid decline, because some drug is coming out and some is going to another compartment, and the tissue concentration is going to be here. Tissue or in the peripheral compartment, initially there is no drug, and then it goes up, and then they meet. These two meet. This is when there is an equilibrium between central and tissue compartment. I had an animation, but this is not. So at one point they will come to an equilibrium, and this is called pseudo equilibrium. At this stage, the drug concentration in the peripheral compartment and tissue central compartment are in equilibrium. Okay. So does it make sense, guys? That what is central compartment and what is peripheral compartment? From central compartment, elimination is occurring always from the central compartment, and there is a distribution phase. During the distribution phase, there will be rapid decline in drug concentration. So everybody got this idea a little bit at least? Is there anybody who can say that where the elimination is occurring from which compartment? Central compartment. Let's see if everybody was listening. Charlie, where is he? Yes. So there are two compartments. So what are those two compartments? You see that my computer identified the right person. Two compartments, central and peripheral, and in case of a theoretical assumption, a central compartment, in fact, in our body, which compartment? Which part of the body? If we think central compartment is a part of our structure, what would be the central compartment? Let's see. Abika. Yes.
Blood.
Blood. blood or plasma, whatever you want to say. And then, so in case of what would be happen in the first, okay. So in case of why there is a rapid decline in the drug concentration in the central compartment, why? You didn't pay attention? Good. Because this, if you do not understand this thing, I cannot move forward. Who is it? Yes. You see, there is a rapid decline in the first, in the plasma concentration or in the central compartment. Why?
In the distribution phase when it's going out to the muscle.
Good. Very good. So because of the distribution phase, you have to always imagine the drug is in the blood or in the central compartment and then it is going down. So that's a rapid decline. So next person. Jordy. Okay. So one question I have that what happened initially in the concentration of drug in central compartment? Sorry, peripheral compartment.
It's low.
Very low, yes. And then it goes up. So this curve I was showing, it will come in your exam to identify which curve is reflecting the concentration of central compartment, which one is drug concentration of peripheral compartment. Okay, now let's go to the traditional lecture. This time I am recording so my lecture so that I know who did not answer. Everything is recorded now. So here, do you want me to play that record? No. I will post this in YouTube. Seriously, I will post this. So because there is our university system is too slow and takes a long time, and I post in YouTube and then I put a link to on the top head. So first learning objective, we have to understand the difference between single and multi-compartmental model. Single and multi-compartmental, we have to understand this. Abilin, you have been lucky this time, but you don't know, next time your name may come up. So here then you have to determine what is pseudo equilibrium or distribution equilibrium, and then equation for, we have to calculate the equation of the two compartment, and also we have to understand the volume terms, different volumes of multi-compartment models, and some of those calculations. These calculations are very easy if you understand the concept. So one compartment model, what we have learned, one compartment model, drug distribute, what we have learned so far is we have learned one compartment model. Drug instantaneously distribute in the body, and drug concentration in plasma and tissue reaches equilibrium very fast. So we do not recognize the distribution phase here. So drug concentration in the tissue compartment may not be the same in the drug concentration in the blood. And when we take into consideration drug concentration in tissue changes based on the drug concentration in the blood. So everything is related to the drug concentration in the blood. We do not take into consideration, in case of one compartment model, we do not take into consideration anything but plasma. What is happening to drug concentration in other part of the body, we do not take. So depending on the extent of distribution of the drug and drug concentration in the tissue may be lower, equal, or higher than drug concentration in the plasma. So the bottom line is this. You see, plasma concentration and tissue concentration are same. We consider the tissue concentration, they follow the same pattern. There is one compartment. That means if you think about that tank, there is drug is going into the one compartment, is coming out the same compartment. And you'll see this difference. There is a straight relationship between plasma concentration and time. So plasma concentration falls linearly with time in case of one compartment model. But in case of multi-compartment model, here, you see multi-compartment model, there is central compartment, peripheral compartment. And during this, and this line is called distribution phase, when drug is moving from central to peripheral compartment, and after that time these two equilibrate. Okay, and these two equilibrate, and then elimination always occur from the elimination. Drug is eliminating always from the central compartment. And what is happening at the end of the always when there is an equilibrium, when there is a reduction in the drug concentration in central compartment goes down, drug from peripheral compartment comes to the central compartment. This is how it always remains in balance. So now one question. So assume the drug is working in the peripheral compartment. Okay, I'll come back to this later. Now central and peripheral compartment. Two compartment model assumes a human body has two compartments, and we are always denoting by central compartment is shown by 1 and peripheral compartment we say it is 2. And the central compartment, what are those central compartment? Is plasma tissues where distribution is instantaneous. Drug concentration in the central compartment is the same as plasma concentration, and drug does not exhibit any distribution phase when you sample plasma from the drug concentration, from the plasma for drug concentration. But peripheral compartment takes up drug at a lower rate, and the tissue, then the tissues in the central compartment. So as I was showing in that illustration, the central compartment, all the drug goes first to the central compartment, and the distribution is instantaneous. But peripheral compartment, drug comes a little later, and for this reason, drug distribution from the central to peripheral is first order process. As you have seen, this is a first order process and controlled by the amount of the drug in the central compartment, and redistribution of the drug to peripheral to central. Here, if you go back to this, no, I think here, we think about this is our central compartment and this is our peripheral compartment. So elimination, this is our distribution, and this is for equilibrium. And then here, if you see distribution to peripheral compartment, so here there will be a rapid fall in drug concentration, and then there will be an equilibrium. So for this reason, here you'll see that we have seen there is a concentration here when they equilibrate, central and peripheral compartment equilibrate. So here another illustration is this, that one compartment model. One compartment model, immediately model, all the drug goes instantaneously to the body. But in case of two compartment model, first drug goes in the blood, oil perfused area, and then it goes to the entire tissues. So here the curve is different. That is, this part is called distribution phase. So I will not go back to this text. Let's go back to these illustrations, which is going to be much easier. So here you think about central and peripheral compartment. In case of distribution, tissue compartment. In case of tissue or peripheral compartment, here you have to think the central compartment. There is a rapid fall in drug concentration, and in case of, you see this tissue, this is same like the other one. So always you have to remember the easy trend. And another is going to come like this. So this would be your distribution phase. This is your elimination phase. This is your elimination phase. And here, this is called equilibrium. This equilibrium is called pseudo equilibrium. Here, at time 0, peripheral compartment contains no drug. You see here, peripheral compartment is like that. And then concentration gradient then pushes the drug from the central to the peripheral compartment. And the concentration in the peripheral compartment will start increasing, but the concentration in the central compartment start to decrease. You see here, start to decrease. And this, when they equal, this will be an equilibrium. This is called pseudo equilibrium. And after the equilibrium, concentration in the central compartment start to decrease due to elimination. So if you remember this illustration, this is our, okay, so think about this is and then, so this is equilibrium. So in the first decline is for what? First decline of drug concentration is for distribution, and second decline is still drug continue to decrease here. No? It is for what?
Elimination.
Okay, good. Let's see. Daniel is here. Yes. So, in case of compartment, in first peripheral compartment, there is two decline phase. First decline phase is for what? Distribution. And the second one? Elimination, yes. So first phase is for distribution and second is for elimination. So we now know in one compartment model is always like that. In two compartment model is different. So now for this we have some complication in therapeutic monitoring of drug. I will come back to this later. Now equation for that plasma concentration. For the plasma concentration here of two compartment model, what we had in our one compartmental model, we had what? C0 and C e to the negative kt. This was our one compartment model and everything. So here you see there are two components. That is, you are adding two first order process. you are adding two first order process. First is that first term is for, as you can imagine, first term is for the distribution phase, this one, and second term is for the elimination phase. Okay, and that intercept, A is the intercept for distribution phase, B is the intercept for the elimination line, alpha is the distribution rate constant, and beta is the elimination rate constant. So now if you think about, without going here we have a curve like this. This would be which one? Which equation? A, yes. A e to the what? Alpha t. B e to the beta t. Good. So we have two first order process here. You are adding these two. And by adding this, you can calculate the concentration of the drug. And this is the concentration of, this is the equation for two compartmental model. And there are many bigger compartments, but we will stop in two compartment. We are not going to go further. So, and there are also ways to calculate alpha and beta, but we are not going to learn how to calculate alpha and beta. We are going to learn, you will have your alpha beta so that you can calculate here. So if you say there are two curve, let's see this one. So again, I will ask this question from, although we are not going to do this calculation, how to calculate alpha and beta, you will have your alpha and beta. So here, as you can see, there are two lines. This would be what? This line for elimination or distribution? Elimination, yes. And this would be, if we consider this is another first order process, this would be for distribution. Yeah, because we are just finding this would be distribution. Because you know that this exponential fall we cannot calculate, so we have to make a straight line of this. So and you can imagine this intercept here. Again, this is your beta and this is your B intercept. Again here distribution phase. So to make this thing cleaner, here you have the distribution, the real line. So here you will have one, this would be your distribution phase, this is your elimination, another line, this would be your distribution. Slope of this line, this one would be what? Okay, let's go back to this one. Slope of this line would be what?
Which one?
This one, line B. Slope of this line. Beta, yes. Slope of the line is going to be beta. And the slope of this line is going to be alpha. Okay? Slope of this line is going to be alpha. And if you know the slope, why you don't have to calculate the slope, we'll just give you the slope. So then you should be able to calculate everything. You can calculate concentration anytime. So now I will do another test and then we'll go to a quiz. Why this is not picking up student from our building? Is it? Yeah, okay. Arseny, what is those? Let's go back. So we have this line, beta. This line is for what? Elimination. And what is the slope of this line? Good. And then other line? Distribution and slope of this line? Good. You are focusing today. Good. So let's go back to here. What? Stop it. Okay, good. Let's see how many you got right. Very good. Slope of line A is so. Where's not showing this? So question. Okay, this is also very good. Here, the correct profile for a drug that shows two compartment models. Very good. Everybody sound rested, so everybody is getting their answer correct. So now time to reach the pseudo equilibrium. Here these are easy calculations. You know that first order process, the time to complete distribution elimination phase depends on the half-life of the process. So you can, if you the time to reach pseudo equilibrium, For example, this one, you can calculate using this equation. You have to know alpha, you just calculate using that equation. Again, when distribution is 90%, when you calculate half-life, you just multiply by 3.3, you should get. When distribution is 90%, you just calculate with the t-half, 3.3 times t-half, and volumes in two-compartment model. So we know that we can calculate volume using this equation, and also we know you can calculate using clearance, using volume from clearance and elimination rate constant. In two-compartment model, we have at least 3 volume terms. So one is volume of the central compartment, volume of the distribution phase, and volume of the distribution at steady state. So this would be VC, volume of distribution phase, VC, VD, and VSS at steady state. So, and the volume of the central compartment is the volume of the distribution at time 0 immediately after administration of a drug, will be called volume of the central compartment. And at this time, entire dose is within the central compartment. And as I have mentioned, the central compartment usually are highly perfused organs. And central compartment volume, to calculate central compartment volume, you have to use this equation, and the correct way you use both. You know, the C0 is A plus B, to correct one would be C0 is A plus B. If you remember this equation, Cp is equal to A plus B e to the negative alpha t of beta t. So we have to use this two volume concentration. This is concentration as intercept. So, and C0 at 0 time is going to be A plus B. Okay, so here always you have to remember this equation, this C0 is equal to A plus B is not going to be in your equation sheet, because we are giving you this A to the negative alpha t plus B to the negative beta t. So how it is A plus B? If you put 0 here, it becomes automatically A plus B. Does it make sense? Because if you put 0 here, this become 1 and then A plus B. So this equation is not going to be in your equation sheet. Your equation will be there, the other one. So volume of the beta area, you can calculate volume of the beta area, the distribution phase. So first is central compartment, and the volume of the beta area, that after the distribution, this when drug distributes and increases, and volume of distribution also increases. And this B beta is larger than BC because this takes account into also tissue compartment. So B beta, the volume of the beta area, which is this one, always you have to remember this here. So this area, it is bigger. So here BV is calculated from the using the following equation. You use CL, clearance. This is all, this equation, all equation comes from here. You see this equation? Everything comes from here. CL, KV. Here, what you're changing, instead of K, what we are using here? Alpha or beta. We are using alpha or beta. So if you are using distribution, we are going to use, if you are using You see here, this is alpha, beta. So this is same as this K every time. And also, I'll come back to this again. So here you can calculate by using this following equation, and the volume at steady state. At steady state, always loss of drag from the elimination will be matched by the gain of drag from administration. So true equilibrium will exist between the compartment when volume of distribution is this: central plus when volume, and BSS, which is volume at steady state, is a true pharmacokinetic parameter that reflects only distribution, is not influenced by the elimination. So, and this VSS relate blood concentration of the drug with the amount of the drug. This drug concentration in the blood with the amount of drug in the steady state. And this following relationship is like that. This beta area is bigger than BSS, volume of steady state, but volume of steady state is bigger than central compartment, the volume of the central compartment. So this is when, if you remember that, the which one is that VSS is the true pharmacokinetic parameter, and a true equilibrium will exist between the compartments when the volume between the compartment and the volume of distribution is this one. But we usually use VSS, the volume at steady state concentration. Now to calculate clearance, as you know, we can calculate clearance using this equation. Here, see this to calculate clearance, and also you can calculate these two equation will come. For example, if you have the dose and IUC, you can calculate clearance. If you know the K and V, you can calculate clearance. Another, you can calculate AUC from this equation. It is C0 divided by K, and I think first few lectures they have covered this. AUC is equal to C0. Now, in case of multi-compartment model, same thing. You see, AUC, if AUC has to be AUC of both volume, your AUC has to be this one plus this one. So this A by alpha is the AUC of the distribution phase, B by beta is the AUC of the elimination phase. So if we use one of them instead of adding both, there will be your AUC would be incorrect because you are not taking into consideration one part. So for example, if you use this one only, forget about this one. You have collected data and you calculate. So you are not taking into AUC of distribution, the elimination phase. You are using only distribution phase. Or if you use this one, you are not taking consideration the distribution phase. For correct AUC for two compartmental model, you have to add both. So these calculations are based on these equations mainly. As I have mentioned in that data point, we try to avoid multi-compartment kinetics because most drug distribute very fast. But when drug distribution is multi-compartment, two compartment model, we have to do some changes. I will come back to this. Here, so correction when you use one compartment model instead of two. So you are using, most of the people are familiar with the one compartment model. So what you are going to do, if you use this, it should be incorrect. Even if you use this VC, if you using this AUC, if you calculate now dose, it will be also incorrect, or volume distribution. When you
See what you're writing.
what? You cannot see the writing? Okay. So here, first, let's go back that. Does this make sense? Why it will be incorrect? Why? If we only use this B by beta. So using the smaller AUC to calculate clearance will give an inflated clearance. You see, if you go back to the clearance equation, this AUC is going to be smaller if you do not use, for example, A by alpha, because you are excluding a fraction of your AUC. Now, if you want to calculate using this AUC, which is smaller, and you fit into this equation here, a smaller AUC. For example, here, real AUC is this, no? A by alpha plus B by beta. Okay, real AUC of two compartmental drug. So now you have excluded this one. So what is going to happen to CL clearance? Is going to higher? Yes, because you see here these are fixed. If you give any smaller value, you will have a inflated overestimation of clearance. Okay, so if your clearance is overestimated, you will have your volume distribution will also overestimate. When you use this VC, the volume distribution will also be inflated if you disregard the initial phase. So if you use only this part and you disregard this phase in the calculation, if you use this part, so your volume distribution and clearance will be an overestimation, and for this you have to do this some correction. Again, this is not in your equation sheet. Incorrect value minus correct value divided by correct value. It is not in your equation, so you have to remember this, because this is common, that how to find out percent error. So now plasma concentration time curves of 1 and 2 compartmental model. As you can see, in case of IV, this is all we have been discussing. This is IV. Okay, this is one compartment model, and 2 compartment model is going to be like that. In case of oral is kind of tricky. When you are taking, it is very hard to figure out this, because absorption is so slow, it may mask the distribution phase. This oral is going to be an IV bolus. One compartmental drug will show this, but 2 compartment will go down and then it come back. These are 3 types. So if you oral, IV, we have discussed mainly IV, which is easy to explain. If you go oral and IV bolus is going to be more complex. So now let's go back some application. What are those problems? The loading dose and site of action. I'll come back to this later, perhaps in the next class. So plasma sampling of multi-compartment model. For a pharmacist who are supposed to monitor drugs, and think about one drug which is digoxin or lidocaine. This drug shows multi-compartmental phenomena. Okay, so if, for example, And we know this is what? Central compartment. This is your peripheral compartment. Peripheral compartment. So now, one option, you are sampling blood. In case of drug, how we monitor therapeutic concentration of a drug? Which central think about, we have given digoxin to answer. So now we are monitoring his therapeutic concentration of the drug. We know the drug digoxin works in the central, this area. Okay, that means it is tissue compartment. What we can do, there are two options. One, we just take his plasma concentration and determine that when the peripheral concentration comes, for example, when it's pseudo equilibrium. Another option is we cut him and find out the heart, brain, everything. We take sample from his heart, sample from his liver, see where the drug goes. But we cannot do that. So only way we did monitor therapeutic concentration of a drug from where? Where? Therapeutic concentration of a drug we monitor from which sample? Plasma sample. So for this reason, when drug has two compartmental pharmacokinetics, this becomes complex. So here, for example, for drugs with multi-compartment kinetics, drug plasma concentration, for example, lidocaine, and the tissue concentration is digoxin, may elicit therapeutic concentration. But digoxin takes 6 hours after IV and more than 10 hours to reach the pseudo equilibrium. So what is going to happen? Because assuming that if you know that digoxin works in tissue compartment and we are taking sample during first 6 hours, is it going to give the accurate concentration? Here, let's go back. You have administered digoxin. We know digoxin works in this area. Find the concentration. Digoxin. But we have taken sample during this time, which is it takes 6 hours. So is it going to reflect the accurate concentration of the accurate therapeutic concentration? No, it is not going to. So for this reason, we have to wait 6 hours to take sample, because when there will be equilibrium will come. Because so for this reason, plasma concentration before the do not elicit any effect may be misleading before the equilibrium. And for this reason, digoxin samples are collected after the distribution phase. Digoxin sample will collect after distribution because digoxin works in the central peripheral compartment. So when a drug elicits its action in the peripheral compartment, then post-distribution concentration will reflect the therapeutic concentration. For example, in case of digoxin. Digoxin site of action is the peripheral compartment. So, and for this reason, digoxin serum levels are monitored at least 4 hours after IV dosing, 8 hours after oral dosing. Does this make sense? This question will be also a concept question. Digoxin, this is very important for pharmacists. So I wanted to make sure that you guys understand this. Yes.
Why is it 8 hours for oral?
Oral takes long time.
So your previous slide said 10 hours.
Oh, 10 hours. This is less than, is more than 10 hours, but 8 hours is the practice. But don't worry, there will be no, the number is not going to be an issue. So here, so our digoxin drug, we know it works in this area. Okay, digoxin works here, and the distribution is, IV distribution is 6 hours. So what is going to happen if we take sample during this time? Okay. Sandy. Yes. So if we take sample, drug plasma sample here, is it going to reflect accurately the therapeutic concentration of the drug or not? What? This area. No, why? What? Okay, I'll ask somebody else then. Evelyn, you did something. Why is not coming? Is happening? Okay, good. I thought you hacked my computer. Every morning I check this if everybody is there. So here, Brandon. So is Brandon there?
Yes, sir.
Yeah, okay. So I was telling that digoxin's the action occurs in the peripheral compartment. Digoxin site of action is peripheral compartment, but digoxin takes 6 hours for the distribution phase. So now if you take sample before 6 hours, during this 6 hours, are you going to get accurate reflection of the therapeutic concentration?
No.
No, why?
Hasn't distributed fully yet.
Yes, it has not distributed fully yet. It has not gone to the peripheral compartment. So for this reason we cannot do. So for this reason you just have to wait 6 hours. Good. Let's go back to my question. Good. Very good. So it's peripheral compartment. Those who have written A, that's not correct. Now another question about digoxin. For therapeutic monitoring of digoxin, serum levels are monitored at least 6 hours after IV and 8 hour. Digoxins. Okay, so distribution phase, 4 people still missed. Okay, if you have missed it, please read these slides again. Okay, now we'll go to our sum calculation as much as you can do, and then on Thursday I'll go back to the sub concept question again. So here we have that following coefficients and rate constant. As always, as you see, you do not have to calculate alpha and beta. You will have your alpha beta value there. Okay. So terminal half-life and distribution half-life. How would you calculate terminal half-life, distribution half-life?
Over beta.
Yes. How would you calculate? This is very simple. I'm not going to go over this. Okay, here to calculate, you know that T half, how T half works, no? And as Adam said, 0.693 by elimination. What is the elimination rate constant here? Can everybody see this, or you want me to increase the slide? Okay. And then what would be your distribution half-life? Distribution half-life would be and the another half-life, distribution half-life would be, which one you will use here as K for distribution half-life? Alpha. So another T half is going to be 0.693 divided by there's something wrong. Oh yeah, so this is oh, there should not be here any. So distribution half-life and that plasma concentration at 1.1 hour. For this you have to use that equation. Plasma concentration at 1.1 hour, you have to use this equation. Cp is equal to A negative alpha T plus B beta T. Okay, so here your A value is there, alpha is there. What is your T here? Yes. Avelin, has anybody that answer to that problem number 3? Plasma concentration at 1.1 hour. You know already alpha is there, A you have there, B is there, beta is there, and T is, Brandon, what is T here? 1.1. Good. So then you have to just calculate. So that lady is Carly here in the front. What is your answer? Abelin. 3.76. Did you get those 3.76 too? Who got 3.76? Yes. 3.76 is the answer. And the plasma concentration at time 0. This is even easier than this. The earlier one. Plasma concentration of time 0 is?
Is that A plus B?
Yes, sir. A plus B. It is A plus B, and you will not have that equation. It is same thing as the equation, this equation. If you put 0 here, in case of, for example, alpha times 0, beta times 0. So this will become, this part will become 1, this part will become 1. So it is A plus B. So now apparent volume distribution of central compartment. The volume distribution, apparent volume distribution of central compartment B, C. So volume distribution of VC, you have to calculate the central compartment volume. VC is equal to dose divided by C0. You know what is C0? So dose divided by what? A plus B. This would give you my central compartment. And then total plasma AUC, as I was talking about, the total plasma AUC would be AUC is equal to, it is total A by alpha plus B by beta. This is easy to remember. Always alpha goes with A, B goes with beta. Even it is multiplication, division. So this is your total AUC. Has anybody calculated total IUC and what is that? 47.5. Those who are not participating, you know that this you have to do in home anyway because of the assignment, no? So if you spend this time now, it will save some time at Sunday night. I'm pretty sure. So I think that's the reason I am doing this, so you do not have to, one of the major concern of the student that this takes so much time at home. So that's why we are going over all those stuff. So you do not have to spend much time. You go over this stuff, and I will post an assignment video again if you want to watch. So with this, I will stop. And on Thursday, I'll finish this and start new material.